Okay, let's dive right in with a question that sounds almost silly. Does the order you do things in really matter? I mean, really? Well, it turns out the answer isn't just yes, but that yes can literally build the world around us.
So let's explore this with a super simple thought experiment. Imagine you've got two basic commands, turn and move. We're going to see what happens when we do both, but we'll just switch up the order. It shouldn't make much of a difference, right?
But look at this. On one side, we turn first, then we move. On the other, we move first, and then we turn. And whoa, even though we started at the exact same point and did the exact same things, we are not in the same place. This gap, this little difference right here, that's the mystery we're going to unravel.
To really get to the bottom of this, to measure that gap precisely, we're going to need the right tools. We need a language to describe not just one specific path, but, all the possible ways something could move. And for that, we turn to the beautiful language of mathematics.
First up, we need something called a vector field. Honestly, the best way to picture it is just as a map of the wind. At every single point in the sky, there's a tiny arrow telling you which way the wind is blowing and how strong it is. It's a complete map of all potential movement.
Okay, so if the vector field is the wind map, what happens if you drop a leaf into that wind? The path that leaf takes, the journey it goes on as it follows those instructions, well, that's what mathematicians call a flow. It's the actual trail you blaze through that map of possibilities.
All right, now that we've got the lingo down, vector fields and flows, we can cook up a really specific kind of journey, a clever little path designed to trap and perfectly measure that gap we saw at the beginning.
So here's the plan. We're going to follow the instructions from one vector field, let's call it path X, then we switch and follow a different one, path Y. After that, we do something kind of sneaky. We go backwards along X and then backwards along Y. Now, logically, that should cancel everything out and bring us right back home, right?
But here's the kicker. When the order of those movements actually matters, you don't end up back where you started. There's this little leftover bit of movement. A gap just appears out of nowhere as physical proof that the path you took changed the destination. And this, of course, leads us to the big question. Is this gap just some random quirk, an error, or is it predictable? Is there some kind of rule, some deep mathematical law that can tell us exactly how big that gap's going to be and which way it's going to point? Well, the answer is a resounding yes, and it's one of the most elegant and frankly coolest ideas in all of math, a tool that was literally invented to solve this exact problem.
It's called the Lie bracket, and its entire job, its whole reason for existing, is to take two of our vector fields, X and Y, and calculate the precise error you get when the order is switched. It is the perfect mathematical measuring stick for path dependence.
And here is the absolutely brilliant reveal. The physical, tangible gap that you can actually see and measure after taking that special journey is exactly equal to the number you get from the abstract Lie bracket formula. They are the same thing. One is just the picture, the other is the math. So a gap appears. So what? What does it actually mean if this Lie bracket isn't zero? Well, this is where things go from just being interesting to being genuinely world-building.
Let's start simple again. We've got two directions we can move in, X and Y. You can think of this as a simple two-dimensional world, like a flat sheet of paper. You can go left-right, and you can go up-down. That's it.
But what happens if that Lie bracket, that little leftover gap we measured, what if it points in a direction that isn't just some combination of X and Y? What if it's trying to point out of the page? The system has a problem. It's created a new kind of movement that it doesn't have the language or the space to describe. To fix this, the system has absolutely no choice but to expand. It is literally forced to invent a whole new third dimension just to have a place to put this new direction. Just let that sink in. The simple fact that order matters creates a new dimension.
And what's incredible is that this mathematical engine doesn't just predict that things have to grow, it predicts the very specific, elegant shapes that have to emerge because of these rules. Just take rotating an object in your hands. Your phone, a coffee mug, whatever. Rotating it forward and then sideways is definitely not the same as rotating it sideways and then forward. Try it. That difference, that gap in where it ends up pointing, that's a rotation around the third axis. The fact that X and Y rotations don't commute is what defines the Z-axis and locks our universe into being three-dimensional. Okay, let's look at a totally different kind of constraint. What if we have three different directions we can move in, but we add one simple rule? They have to stay on a flat plane, and they have to perfectly balance each other out. So the rule is simple.
Written out in math, 3 directions, all the same strength, must add up to 0. They cancel each other out completely. It seems like a minor detail, but this constraint has a stunning and totally unavoidable geometric result.
The math is just unforgiving on this one. The only way for 3 equal forces to cancel each other out on a flat plane is if the angle between each of them is exactly 120 degrees. It's not a suggestion, it's a mathematical necessity.
And what pattern in nature is absolutely defined by 120-degree angles? The hexagon. That simple little balancing rule forces the system to create a hexagonal grid, one of the most common and efficient patterns we see in the entire natural world, from a honeycomb all the way to graphene. So this brings us to this really beautiful, unified idea. That physical gap we saw from just turning and moving, the abstract math formula of the Lie bracket, and even the curvature of space itself. They aren't actually different things. They're just 3 different languages describing the exact same fundamental truth about our universe.
And this leaves us with a final, pretty mind-bending thought. If something as basic as the order of operations can literally build dimensions from scratch and force nature into using specific geometric patterns, what other fundamental structures of our reality are just sitting there, hidden in plain sight, dictated by simple rules we haven't even thought to question yet?